Let me add my personal welcome to all of you. It's an exciting day. I hope that the program that we've put together will share with all of you a bit about the past, but really the inspirational future that is held in SLAC and all of those of you who are part of this great institution. It's my real privilege and pleasure to open the symposium formally with the first speaker. Paul Alivasatos is, well, let me say just a little about him, not too much. Received his bachelor's degree in chemistry from the University of Chicago and his PhD in 1986 from UC Berkeley. He spent a short time postdoc at Bell Labs and then joined University of California at Berkeley as a faculty member in '88. He's currently a professor of chemistry and material science and is also the Larry and Diane Bach Professor of Nanotechnology. As all of you know, Paul is director of the Lawrence Berkeley National Laboratory. He's leading the laboratory in innovative new R&D areas, looking forward really to the future, sustainable energy and efficiency and climate change, just to name a few of those. I first met Paul, he's smiling, he'll remember, on the experimental floor at SSRL many years ago. He was using X-rays at that time to look at a material that wasn't so in vogue or in fashion or understood. It was nanocrystalline materials, and he was studying the physical and chemical properties of those materials using X-rays. In the subsequent years, he has made tremendous contributions, seminal contributions, to the understanding of nanocrystals, nanocrystalline materials, their properties, and equally importantly, how those properties can be translated into important applications in areas like biological imaging and others, actually. Paul is a recipient of many awards and prizes. I won't list them all, just mention a few. The E.O. Lawrence Award from the Department of Energy, the Wilson Prize, Israel's Wolf Prize in Chemistry, and he's also a member of the National Academy of Sciences. So it's a real pleasure to welcome Paul to give the opening talk in this SLAC 50 Science Symposium on nanoscale material science. Paul.
Good morning. It's such an honor and pleasure. Is my mic on? Can you hear me okay? Yeah. It's such an honor and pleasure to be here with you this morning and to have an opportunity to talk with you about the area of nanoscience. But first, I would like to say greetings from Berkeley Lab, wearing my lab director hat, and to say that the incredible history of the discoveries that have happened here at this laboratory have truly changed the face of science. And it's really a great moment to be able to celebrate those many accomplishments, as well as to celebrate the spirit in which they were performed, the openness with which this community has fostered the development of great breakthroughs. So I would like to thank you for that, and also to say that there has been a partnership between Berkeley and Stanford from the very beginning, and you can see here Louis Alvarez with PIF from their days both at Berkeley and subsequently interactions here at SLAC, where the cooperation between our two institutions has always been strong, and I think in the coming 50 years will be actually just as deep and just as meaningful as it has been in the past. So I'm very excited about that. I was asked to speak a little bit about the future of nanoscience, and my goal in this will be to use the topics of energy and environment, the problems of energy and environment, as a springboard to help me explain a little bit about what the foundations of nanoscience are today, and also what the opportunities for nanoscience are going forward in the future. And one thing that we certainly know to be the case is that in coming decades, problems of energy and environment are going to be critical ones for the future of humanity. And a national laboratory such as this one will undoubtedly concern itself very deeply with topics of energy and environment. That's going to be a big piece of what we do in the coming years. And so you will see that we'll be thinking a little bit about how labs can organize themselves, and also how, if we do create new solutions in the area of nanoscience, how can we ensure that they don't in turn just create new problems of their own, is something that we'll be trying to think about a little bit. And so certainly you all know that the problem of the imbalance of the carbon cycle is one aspect of the energy and environment problems that we will be encountering as we go forward. The 32 gigatons of CO2 emitted each year, half of which remains in the atmosphere, is in fact altering the climate of the planet. And we need to look forward to creating a future balanced carbon cycle in which we have access to energy while at the same time being able to preserve the emissions of carbon to not knock the CO2 out of balance, or to bring it back into balance over time. So we'd like to find a future balanced carbon cycle. And at Berkeley Lab, there's a program that involves a set of initiatives in the areas that you see up here. We're calling it the Carbon Cycle 2.0 initiative. And it has features of all of these topics: combustion, energy storage, especially energy efficiency. All of these are different parts of what we think of as being the science for the future stable carbon cycle. And what I would like to talk with you about today is nanoscience, and I'll take three examples. The example of energy storage, artificial photosynthesis, and carbon capture and sequestration. And I'll try to show how nanoscience can contribute to solutions in this area, and also show how this area poses challenges to nanoscience that are far beyond, actually, in some ways, our capabilities today. So we're going to have a long run at some of these problems. So the themes of nanoscience that I would like to emphasize to you will concern the foundations that we have already. And those are the scaling laws for nanomaterials and the synthesis and properties of building blocks. These are two things that we know an awful lot about today, following the last 20 years of intensive work. But then you will see that we have a very deep connection to biology, from which we are learning and to which we can contribute. And that's a very active process as we go on today. And we are in an era of building more complex systems. So I'll try to take you through that sequence of events that this field has been through. And we're going to go back to what we consider to be the beginning, and that is the first nanoscientist. That's Democritus. This laboratory, of course, is famous for taking atoms apart and looking at what's inside the most fundamental constituents of atoms. But in the nanoscience world, we think of a thought experiment of Democritus as laying, in a sense, the groundwork for our field. Democritus, of course, you'll be familiar, was the first person to use the word atom, meaning indivisible, which he arrived at by considering what would happen if you took, for example, a piece of gold and chopped it in two. And he reasoned that if you took a piece of gold and chopped it in two, you would have two pieces of gold. It would be the same thing. If you measured its fundamental properties, its density, its melting temperature, they would be the same. And then, for some uncanny reason, he was able to continue to think about that successive division process, and to imagine if you kept chopping it in two, at some point you would arrive at the graininess, the inherent graininess of matter, and you would find that it could not be chopped any further. Therefore, the atom, that which cannot be divided. It turns out that in nanoscience, we look at those last 4 or 5 divisions just before you get down to a true atom. Okay? So we might have, let's say, 1,000 atoms, a few hundred, a few tens, and we look at the properties of matter, and what we find is almost every single property that would be recorded in a textbook as being the properties of a material change when you change the number of atoms at that length scale. And therefore, that's a rich area for discovery. So these are some of the known scaling laws, and I'm going to show you 4 of them in this talk. Melting temperature, structural transformations, energy level spacings, the artificial atom concept, and charging energy. And So let's take a look and see some of those scaling laws in action. The first one is just a warm-up because it's kind of easy to intuit and to understand that it happens, and that concerns the melting temperature. Remember, we're taking a piece of gold, we chop it in two many, many times, we arrive at the point where there's almost as many atoms or as many atoms on the surface as there are in the interior. And so we now imagine, what is it that holds this crystal together? Well, it's the bonding interaction of each atom with every other, but if half the atoms are on the surface, the crystal is essentially weakened in its interaction, and its melting temperature is dramatically reduced. Here's an example of that from work that I was involved in the early 1990s, measuring the melting temperature of a semiconductor crystal material as a function of its size. And what you can see is that if you make the crystal very small, it melts at an enormously lower temperature, which scales roughly like the surface to volume ratio. So that's a scaling law. The melting temperature is reduced in proportion to 1 over the radius. And so that's an easy observation to make in the early days, but it's quite interesting in itself immediately, because it means that you can take materials which ordinarily would be formed at high temperatures, but when they're nanoparticles, they become accessible to processing at temperatures hundreds of degrees below where the normal material would be processed. And that turns out to have a lot of significance. In a practical sense today, what it means is that it's possible to make materials which previously had been made by very complicated and cumbersome techniques. You can make them by very facile, simple techniques that take place in a simple flask. In a manufacturing sense, that means going from, again, very complex manufacturing to being able, for example, within your iPhone to have inks that contain nanoparticles that fuse to make circuits that are on flexible substrates, and prospectively, as we move forward, to have materials that are produced for solar cells or batteries that, again, are printed on large scales. So that's an example of a scaling law. Here's another scaling law that you have each probably encountered at one point in your lives. If you take a trip to the jewelry store, you would like to buy a diamond, and what you will find is that there's a scaling law for the price of diamonds, which is on the De Beers website. Big diamonds are much rarer. A diamond of double the weight costs 4 times more. And that immediately, by the way, brackets the size of diamond you're going to buy. You know, there's a certain, you can't just double that easily. And so there you go. Where does that come from? That comes from the fact that to make a perfect crystal requires annealing out of defects. And the time to anneal out a defect will scale exponentially with the volume of a material. So if the crystal becomes quite large, the probability that any defects that might have been there when it was initially forming will be very, very long the larger the crystal, and therefore it will become a much more rare material, and therefore much more expensive. Okay? What's very interesting about nanoscience is it turns this upside down. And this is one of the key lessons in nanoscience that appears over and over again. The lesson is that if we make very small crystals, it's actually very easy to push all the defects out, and therefore to make them highly perfect. It's the inverse of trying to buy a big diamond. Now you're trying to find little tiny ones. Well, little tiny ones, it's quite easy, because of the melting temperature, to push defects and grain boundaries out, and actually it's possible to make an ensemble of nanoparticles in which there's only very rarely any defect inside the average crystal. So it's possible to make them highly perfect. One way, in fact, and I wanted to show this story simply because it does relate to what Keith said, what I was doing myself here with my students at SLAC in the early 1990s at SSRL was studying phase transitions in nanoparticles. So we took small crystals and we placed them at very high pressure, and we tried to see, would a phase transition occur when you squeeze on it, and we did those kinds of experiments right nearby here. And what we found at that time was that if we took a very tiny crystal, we could often super pressurize it beyond any structural pressure by an enormous amount than anyone had expected, simply because the crystal contained no defects at which nucleation sites could occur to induce the transition. Eventually, the transformations do nucleate at the surface of the crystal, which is a type of weak spot. But it turns out, interestingly, most commonly in the types of structural transformations that we were looking at, defects in the bulk material initiate at much higher energy types of grain boundaries and other defects, which are not present in the nanoparticles. And therefore, they show a qualitatively different behavior with respect to that. You can see the perfection of the nanocrystals there. But another thing that's very interesting about this that's quite fundamental for energy is that these transformations could take place with a 20% volume change of the crystal. The crystal can change from one structure to another with a 20% change in volume and then pop back again and just go back and forth like that, remaining a single crystal. If you take an extended crystal and try to do that, it will break up into domains because as the small domain grows inside the larger one, with the enormous volume change, as the domain becomes large enough, eventually it exceeds the dislocation energy formation in that solid, and the crystal will essentially crack into pieces. That's what happens in a normal bulk material. Is that important? Yes, it shows up directly in energy technology. This is a scaling law now that says small crystals can be quite perfect in their structural transformations. They can alter shape. They can withstand chemical transformation with enormous volume changes. Well, it turns out that shows up very directly in energy storage. In energy storage, we would like to take lithium and put it into a new domain, and the volume has to change. It might change by as much as 20 or 30% when the lithium is incorporated. So Yi Cui, who's here at Stanford, realized that a fundamental scaling law of nanomaterials is that they can undergo these types of transformations, and therefore he took nanowires and showed that they could be lithiated, silicon nanowires, that they could be lithiated, and they could withstand the volume change without cracking and falling apart in the way that a conventional battery might. This is an example of finding how a scaling law in nanoscience then eventually finds its way into the design of a new kind of battery. And in fact, nanotechnology-enabled anodes, cathodes, and even transport media are going to really change battery technologies in dramatic ways. That's built off of that finer understanding of the scaling laws that underlies it. There are many examples of that. I'm not going to show all of them that's on here. Let me come back momentarily to that structural transformation itself. It turns out I wasn't working on it too much for a while, but then the Linac coherent light source started to become possible. And so I have been working with some of my coworkers for a little while to build a system where we could use the extremely fast pulses that are present at the Linac coherent light source to initiate phase transitions and try to observe them as a function of the time to study how fast a structural transformation can move. How does it nucleate? And so recently we were able to get a little bit of beam time. It was, I think, 6 hours at the LCLS. And after getting our proposal rejected 5 times, but only because there's so much excitement about using that thing. But in the first experiment already, we could observe the structural transformation, and we're able to induce it with a shock wave. And I'm just very excited because I think we're going to learn about how transformations occur in nanoscale materials in new ways using the new machine. So those are 2 quick examples of scaling laws showing up in energy. 2 more. Quantum confinement is, of course, the classic one that people study in semiconductors. In a semiconductor, an electronic excitation creates an electron in a hole, which are delocalized there, wave-like particles, and the wavelength of those particles is a characteristic of the semiconductor material in the bulk. It might be several nanometers in size. If you make the material small compared to that normal quantum wavelength of one of those particles, then you will, of course, see the quantum size effect quite clearly. And one thing which Keith mentioned that I've been involved in over the years is the study of how that affects biological imaging. Now, let's take that and add one layer on top of it, which is in the intervening years, going beyond making those quantum effects, we have also learned how to make very, very complex types of nanoparticles. Not just a simple building block now where there's a simple crystal, but over time, people have learned how to make them into structures that are branched, striped, hollow, nested, different topologies and connectivities in many different ways. So we can now start to take the scaling laws of the individual components, but then connect the pieces together to make things. Okay? So that's a very important piece of this area of science. And there's a very famous saying, in which I think a particle physicist might relate to in some ways. It's a saying of Rutherford, who said that there are only two branches of science. There's physics and stamp collecting. Okay? And they, I believe, deserve equal respect. And I'll tell you why. Because if you don't have a good collection of stamps, it's very hard to do the physics that comes later. You have to see the patterns of what is happening before you can then understand what truly underlies it. So in the nanoscience area, we have now made a very big stamp collection of particles of different connectivities and shapes, and they're very intricate. Okay? And we've got that now. We can make that, and that allows us to go off and do new things. So let's take the example of artificial photosynthesis. If we look at a membrane, a photosynthetic membrane, it's a very beautiful, beautiful structure of exquisite complexity. Inside it, in this membrane, are a series of proteins and molecules which act in concert. When a photon is absorbed, an intricate series of events ensues, where charges are separated across the membrane, redox chemistry is driven, there are selective channels that allow maintenance of chemical gradients across the membrane. It's truly beyond the capacity of any nanoscientist or material scientist to build a system at this level, even not to get close. There are so many features of it that are going on that we deconstruct it. One activity that we go through is we deconstruct it all the time and try to understand it. How does it work? But the equally valuable exercise is to try to build your own. Can you make one that would have similar features? And this is a major challenge. So today, there's a whole community of people trying to learn how to make an artificial membrane that would have many of the features that the natural one does. And let me tell you about how you can see a couple of scaling laws show up before we get to how hard the problem is. Okay? So imagine that you're absorbing light, and you want that light to then be used to do some chemical work, to perform a chemical transformation. So, okay, let's say that you have a semiconductor that absorbs the light. I just showed you in a semiconductor, the electrons and holes will delocalize over a large distance. Well, when they do chemistry, I want them to, the electron and hole to go into one bond. I don't want them delocalized. So, okay, I should then make the light absorber really tiny so that I don't have to recompress the electron and hole to a small volume. It can do its work right there. Okay, I can do that, but then what happens? Well, the material now, having absorbed light, I also would like for it to be stable. Remember, I've broken a bond, and that bond, that when I absorb the light, now when that bond is broken, I'd like the energy to flow in a specific way, but I don't want anything to fall apart. Well, if I do it in a single molecule, the odds that it will fall apart are quite high. It will find a pathway that won't work. So I'd like to delocalize the excitation over some length scale. Well, what length scale is that? I don't want it to be too big, because then I'll have to relocalize the charges later. It turns out a few nanometers isn't such a bad guess. And in fact, that's what happens actually in the natural light-absorbing system. It endeavors to find ways to delocalize the excitations fairly quickly and then relocalize them to perform the chemistry. Those are tricks that we would like to learn how to emulate in the artificial system. So we go about trying to build our own little models. So in my lab, we just have our own toy system in which we build with the methods that I've described, a semiconductor rod that has a little component inside of it that localizes holes, another component where there's an electron catalyst, and another component where there is an oxidation catalyst. And all these things are built sequentially in the ways that have been developed over the recent years to control the nanoscale materials. The artificial atom quantum size effect is a key to this because we design the system in such a way that an electron will not want to sit here. When light gets absorbed, the electron will want to delocalize in this structure and therefore go into the reduction catalyst, while the hole will very much want to sit behind here in this zone where the oxidation catalyst is. And then we can try to design and make our own material. A last quick scaling law, and then show you one of the issues that we face. One of the things that's quite tricky in photosynthesis is for the chemistry to keep up with the flux of the photons. Photons come at a fairly regular pace, and we have to try to keep up with it. It turns out there are hundreds of electrons that have to flow through the system per nanometer squared per second. So the catalysis has to keep up with that flux of the photons, and it's not so easy to do. And what one tries to do then is to see, how fast can you make the system have flux of charges through it without anything backing up? Okay? So here's an example of something backing up. We take a system, and which is the nanorods I just showed you. They absorb light, electrons come to this catalyst, there's another catalytic particle over here, and we just shine more and more light on it. We just turn up, in this case, the laser intensity, and we just see when does it start to saturate. And what we find is that at a certain power, the system no longer is able to keep up with the flux of photons. Oopsie, sorry. And where is that? And that'll just give you a feeling for the type of problem that one wants to solve. In this case, when photons are absorbed, eventually we reach a point where an electron comes onto this metal particle here and will be used to reduce hydrogen, to make hydrogen gas. If that chemical reaction is slow, then eventually another electron will try to arrive before the first one has gone. And at that point, the chemistry is no longer keeping up with the flux of the photons. And it turns out you can't get more than one electron onto a tiny metal particle. That's my last scaling law. I'll teach you very quickly. It goes like this. If I have an electron and I stick it on a piece of metal, I've increased the electron density by 1 charge over the volume of that metal particle. If I try to stick a second one on, it has to overcome that Coulomb repulsion. If the particle gets smaller and smaller, it's the same 1 electron, but the Coulomb repulsion is, of course, much larger. So if I have a very tiny crystal, I'm trying to get electrons to fly through it. I can't do that necessarily to keep up with the flux at which the photons are arriving. So you can see those are examples of the kinds of things that would end up in the design of an artificial photosynthetic system. Today, DOE has established the Joint Center for Artificial Photosynthesis, and they're taking a systematic view. I showed you a toy system. They're making real systems, and they're solving the problems of stability and earth abundance. So for example, in some recent very exciting work from that place, they found that, for example, they can take a semiconductor indium phosphide, which is terrific as a light absorber for artificial photosynthesis, but normally completely unstable. But they can perform a very careful coating with a very thin layer of TiO2, rendering it stable for an extended period of time. So that opens up a kind of light absorber that's very, very important. Likewise, they found a way to make a oxidation catalyst that is also quite stable from earth-abundant materials. So there's a kind of a rapid set of discovery of components, but then there's also the process of trying to integrate all of those components together and build them into a system. And that, I think, is one of the really big challenges that we face today. A last topic. So fundamentally, what happens in nanoscience is this idea of design using scaling laws, build on the nanoscale, but then there's another piece to it which is very important for us, and that's the piece of measuring at the level of single molecules. And this is the reason why we have to do this. It turns out that in nature, when nature is building components, it has developed an incredible synthetic capability that allows the precision at the level of atoms to be exact, so that a protein can be made to have an exact number, even if the number of atoms is 100,000. Every atom in a structure is in the right place. Maybe it fluctuates, but they're, you know, in a sequence, it's all established. If we try to make a structure like that where every atom is in an exact position, we can do that up to a certain number of atoms, a few hundred maybe. When you get beyond that, actually, we only work with averages. We're not able to make every one exactly the same as the next. No one knows how to do that. There is no technology for doing that. And so that's why we have to go in and look particle by particle or molecule by molecule when we make them artificially to see how does this one behave versus that one, because they're not truly all identical. And until we learn how to make them identical, we won't have that. So here's an example, just a quick last example of some cases where we're developing new methods for looking at the nanoscale. And this will be the last thing I'll show. Recently, and I'm showing it partly because it allows us to give you a case where the nanoscience itself feeds in to help it grow. One of the most interesting materials discovered in the last several years has been graphene, a single sheet of carbon. Nobel Prize in Physics just given for it a couple of years ago. Well, it turns out we can take graphene and use it as the window for a cell in an electron microscope. So we have a little pocket of liquid encapsulated between two single atomic thick layers of graphene. And now when an electron microscope is used to penetrate through that, the contrast is terrific, and we can image nanoparticles inside a liquid as they do their business. On this view graph, they're growing, they're connected by DNA and moving around, or we're able, in fact, to go particle by particle and look at their structure. There's one particle as it's rotating inside a liquid. We're able to collect the electron diffraction pattern from each position and orientation, and therefore we should be able eventually to obtain the position of exactly every atom inside that specific particle. Remember, the next particle isn't atomically identical, so now we think we can do that, and that will be very exciting for us. We're going to just wrap here and go, if I may, to just a last slide so that there can be a little time for questions. As always, I was a little ambitious thinking that I would say some more things, but I'm not going to be able to do all of them. I just want to go back to the themes of nanoscience. I hope that what you've seen, nanoscience is built off of scaling laws. And we use those scaling laws to estimate, to calculate, to design, and then we can try to go in and see, are they correct? And today, we have learned already through the last couple of decades how to make building blocks of different types, all different kinds of materials with different shapes and connectivities and so on. So we have a set of building blocks, and we have the ability in many cases to observe them at the single particle level. And we have the biological sciences which provide for us an inspiration, because the biological systems do things so far beyond what can be done in any normal synthetic process that people know how to do. So there's a deep connection there for us, because we're able to operate at the same length scale as the fundamental units of biology, but we're building our own. And there's, of course, this very famous phrase of Feynman's that really animates this type of thinking, who said, "What I cannot create, I do not understand." And that's one of the great challenges that nanoscience is going to be facing in the coming 50 years as it tries to learn how to emulate biology and build systems for energy conversion. I think I'll wrap it up there, and thank you.
Sure. Okay. Opportunity for questions, and there are microphones which will be brought to you. Helmet, the microphone over here, right here.
Paul, fantastic talk, of course. My question is, you didn't say anything about the role of simulations. What
Yes.
role? What
Yes.
role do you see there?
Yes, I really should have said a lot more about that. Actually, it's in a fascinating stage at the moment. For the first time, I would say, in recent years, we've entered a mode where computation of the properties of materials and of nanomaterials as well has reached a point where it is both accurate enough and fast enough that it's possible to engage in the design of these components really in the computer. And I didn't give that enough play in this discussion. I really should have, because it turns out that it's gone beyond the stage now of, well, I have an observation, I'll try to talk with a theorist friend to see if they can be brought into order, to the stage where the computer modeling and the theory that underlies it has become capable of surveying and predicting to a much deeper level than ever before. So it's a key piece of it. Yeah.
I'm reminded of a great physicist from the earlier century, Lord Kelvin,
Yes.
who said, I do not understand anything unless I can create a mechanical model of it.
Mm-hmm.
We've advanced a long way since those days.
Right.
Malcolm Derrick at Oregon.
Right.
Paul, you talked a lot about scaling laws, right? But scaling is something that, you know, physicists might or might not relate to very well, right? Scaling, the 3 cars and they're all green coming in a row, and the scaling law is, you know, there's only green cars. So how do the scaling laws, will they ever end up to be, you know, a precise, predictive, you know, system that we have now on a very fundamental scale for physics?
Well, so what I would say is the scaling laws are fascinating because they're the back of the envelope start of the discussion, and we can understand them, and we can use them as quick guides, how to think about problems and get into them, and so on. It turns out for every scaling law that I showed, there is a little universe of people who study them, the specific ones, and amend them and correct them and are able to find the exceptions and the different ways in which they are not quite exactly right, but are in fact, you know, just a little bit not quite right. And that's a good exercise, and I support it very much. I do some of it myself occasionally, but I'm not as good at it as some people, so, you know, I only do it occasionally. But it's a fascinating exercise to do. So, you know, the scaling laws are there really to help us think in a qualitative way. But it's amazing to me how often it will turn out that when you see the final experiment, you can understand how it came out using those. You know, it's amazing how often that does turn out to be the case. Yeah.
One more. See somebody's here in the middle.
Yes, Mike Grissom, SLAC retired. My question deals with 2 confined space issues that are operationally very significant from organizations I've worked for before. One is NASA and human crewed spacecraft, and the other is U.S. Navy for submarines. In both of those processes, you produce a breathable atmosphere with energy-intensive processes, and you have to sequester carbon as well using chemical processes. I think they'd be very interested in knowing if we have some practical applications of actually using the carbon in a photosynthetic-like process to generate oxygen for long-term spacecraft transfer.
Okay. Well, I don't know enough about that specific problem to answer the question on the spot, but what I would say is that there's the community that's studying the processes of how fuel cells and the inverse of them, like these, are, is really, that area is developing quite rapidly right now. There's a lot of really neat things happening. New catalysts have been found in the last few years that are quite impressive, and the ability to engineer how the components move through the structures, the chemical components move through them, has improved a great deal. So, there was a big push in areas like these. In fact, since you mentioned the space program, there was a really big intensive push in areas like that during the era of the space program. And then in the sort of, 1980s or so, it really kind of was backburnered for a while. And it's come back again recently as a really intensive topic of discovery. So it's worthwhile to go back and reinvestigate some of the earlier, try to apply onto them the newer ability to control matter and see how it can be, manipulated. Yeah.
No more questions? Okay, let's thank Paul again.